All right, good morning. You start off by, I put the exam review page under the meeting chat. So just want to kind of highlight a few things from the fall exam page. At the top, I think the summary sheet is a helpful thing to have, so feel free to print that out or have access to it. You can have that to use on your exam. Yesterday, I sent out a message through Remind. Just wanted to have you guys let me know whether you plan to take the exam or not by filling out the survey form. So here is what you should see on your end on Infinite Campus. If you are taking the final, then the assignment should show up in Infinite Campus as final exam. But if you are exempt, then it should not show up for you. It should, you shouldn't have to, there's nothing to put in for a grade, so it should you should not even see it when you're on Infinite Campus. So if you are in one category and you want to be in another, just let me know and I can change whether you decide to not take it. You let me know, or if you are signed up as exempt but you decide that you want to take it, you can let me know as well. But I need to know by end of today, since I need to plan out distributing the exams to students who are taking it. Okay. So scrolling through here, today we're going to be looking at mainly kind of chapter 5 review material. I had a health session this morning, and I'll have another one this afternoon, going over review packet 2. It'll be face-to-face as well as recorded on Teams. And here are the links for packet 2. Tomorrow's the 7th period exam, but it's still a full day of school. I'll have a help session 7:15 and 3:30, but I'm going to be going over packet number 3. Okay, 7th period exam, and I'll see you guys 4th period. The schedule is scrambled a bit. First and second period are now at the end of the day. Wednesday, I'll have a health session, 7:15 and 3:30. And then on Thursday, health session, 7:15 in the morning. So you guys will take your exam second half of the morning. 10:25 to 12:20 is the exam period, but the exam is only 90 minutes long. So it'll be released on Teams 10:25. You'll take it from 10:30 to 12, and the exam is due by 12:05. Now this will be on Teams for virtual students, but face-to-face will be with me in the classroom. 3:30 in the afternoon, I will do a trig quiz review for any students who want to do a recovery on that trig quiz. You can recover up to an 89. There is a Teams assignment requiring these prerequisites to be done, such as your classwork, your homework, quiz corrections, as well as assignment from the textbook. And then that trig recovery quiz is going to be 4:30 on Friday. All right. Any questions with what I've gone over here? Okay, so let me spend a few minutes going over exam details, see if you guys have any questions there. Okay, so I went over your time as 10:25 to 12:05. Virtual students will take their exam on Teams, but face-to-face students will take the exam in the classroom. There's penalty for late submissions, so you want to make sure that you can get, if you're on taking virtually, that that you are submitting it by 12:05. Okay, otherwise it will be penalty. Multiple choice answer form is going to be the last page of your exam, so you're going to complete it at the end. Show work where suitable. On the test, on the exam. Not every problem is going to require you to show work, so if you're reading a graph, you may not show any work. But problems that do require work, whether it's product rule, chain rule, or implicit, I want to see all that for full credit. Okay. But if you're showing showing a knowledge of that concept, but then you just happen to miss the problem, I'll look to give you partial credit. Open notes, bring your calculator, use your calculator. Curve is going to be applied on this exam. Still don't know exactly what that will be yet. Have a better idea tomorrow after the 7th period exam. This will not impact your grade negatively. And then virtual students will take on Teams, and yeah, again, face-to-face students are going to take it in the classroom. Yes, question.
So hopefully not. Like if we didn't do poorly on the final.
Right, it's not going to go in the grade book.
And that would be so but would that grade still be like entered into the campus so we can see it, or would we like it after break?
Yeah, I think right. So I think if it's not, if I decide that it doesn't help your grade, or it's not good enough to replace your lowest test grade, I'll probably just end up sending you a text remind, letting you know what you got on the exam, but it's not going to go in the grade book. Yeah. Or you can, or if I don't do that, you can just send me a remind, ask me what your grade was. Yeah. All right. Any questions about the exam? So you guys are taking it on Thursday, right? Thursday. Okay, we'll still have class tomorrow. It'll be a little bit short, but technically tomorrow's the last day of class before we go into exams. Good, no questions. All right, so this is what I want us to do today. So we've gone over a lot of these topics for the exam, but today I want to focus on the one I highlighted in green. So we'll do this very specific type of problem, piecewise functions involving continuity and differentiability and knowing what to do with those steps. We'll do a linear approximation problem. We'll do a derivative rule involving chapter 5, like the new rule involving log base A or exponential function base A. Expanding, taking advantage of log properties when appropriate, because we know our derivative is going to be easier to apply the more that we can expand on the front end. Log differentiation. Right. Understanding when to use log differentiation. We'll go over a specific problem and talk about how to recognize the need for log differentiation. And then also finding the derivative of inverse at a point. Understanding that relationship between a function and its inverse in terms of their order pair, but then also in terms of their slope. Okay, so let's start off with, I'm going to pick out a problem from the packet number 1 here. Number 55. I wrote it a little bit larger so you can see makes it easier to read. So if you look at this problem, how this is set up, we have a natural log problem, but this is a rather messy set of terms inside the parentheses, right? So technically we could do u value, but this is a really large u value that we want to take advantage of some expansion properties before we take the derivative. So we're going to expand using quotient and product property. And the first thing to recognize is the fact that there are 3 terms that we can split this up into. So you got the numerator, and you got 2 in the denominator. Your numerator is going to be part of a positive natural log term, and your denominator will be part of a negative or minus natural log term. So I'm going to spend the effort to expand. So here's my first step. Notice that when I split it up, it's already beginning to look a lot easier to handle, right? Granted, you're going to have more problems to find derivatives for, but each of the problems will be a lot easier than the one we started with. Okay, but we're not done with expansion yet, because even though we have 3 terms, within each of these terms, we're going to try to handle these radicals and rational exponents. So I'm going to continue to do a little bit of cleanup efforts here. So radical, I'll rewrite as to the 1/2. And then eventually, those exponents can come down as well because of power property, right? Those exponents are free to move. Okay, so we'll bring that 1/2 in front. We'll bring the 2 down in front. And that's where we want to be before we consider our derivative rules, right? So if you look, each of these parentheses, each of these u values are going to be really manageable and relatively easy from a derivative standpoint. Okay, so I'm going to apply u prime over u for each of these terms. So x squared plus 1 becomes 2x over x squared plus 1. X becomes 1 over x. 2x cubed minus 1 becomes 6x squared over 2x cubed minus 1. And then the coefficients, 2 and the 1/2, will just attach itself to their respective terms. Okay, so there's my derivative. The 1/2 hangs out in front, the 2 hangs out in front, and I can, if I see matching pairs, I can cancel out. Numerators I can combine together, and it matches answer choice D. All right, any questions with log expansion, applying log expansion before derivatives? All right, let's look at 56. this is a problem that requires quotient rule, numerator and denominator, but then also applying the rule involving a to the u. So I'm going to rewrite it a little bit larger here. Again, off packet 1. So if you look at that 3 to the x, understanding that there's a rule specifically for this exponential form, a to the u. So the rule is natural log of a times a to the u times u prime. So let's go through quotient rule, f prime g minus fg prime all over g squared. And when we get to this, the rule for the g prime, we just match the parts, right? My a value is the 3, my u is the x, so just follow what the rule says, natural log of 3 times the original function times the exponent's derivative times 1. So I'm at the derivative stage. I'm done with my calculus. Now I'm just trying to see what I can do to clean up. So between my numerator, looks like I have some common factors I can take out, right? They both have a 3 to the x, and they both have x squared. So I'm going to take out 3 to the x and x squared and see what's left over. If I take out 3 to the x and x squared, I'm just left with 3. If I take out 3 to the x and x squared here, I'm left with x and natural log of 3. And once I have my factors out, then I can look for common things to continue to reduce. Okay, questions there? Right, let's look at number 58. This is not natural log. This is not log base e. This is log base 3. So we have a specific rule for log base a. Looks a lot like natural log. There's a u prime over u, but then there's kind of this added component that has to be part of our derivative. Now, this is also a log expression, which means that if possible, we could also expand, provided that it falls under expansion properties. But if you look, this is not expandable because there's a minus in between, right? Now, if these terms were multiplied or divided, then we can expand, like this previous problem that we did at the beginning, right? These are multiplied and divided. That's why we can expand. But when you have already subtraction to begin with, then it's stuck. We can't go any further if it's in this form. Okay, we identify the u value to be what's inside the parentheses. We apply the rule 1 over natural log of a times u prime over u, and it should be a pretty straightforward answer here. Okay. Any questions there? Okay, let's look at a problem like number 60. Well, actually, before we do 60, let's do a log differentiation problem. So I just created this first period, so I'm just going to have you guys copy this down, and we'll go through it step by step. Now, this is a problem that requires log differentiation, but if you see it on the exam, it's not going to say apply log differentiation. We have to be able to recognize the need for it. So this is how we can tell. You can tell that this is not power rule, right? Power rule is going to be, if it was chain rule, then you can have a base that is a variable, but your exponent is going to be a constant, right? Then you can do chain rule. But this is a variable raised to a variable. And also, it's not just a constant raised to a variable, right? If it was 3 to the 4x, then we can apply the a to the u rule. But this is a variable base raised to a variable exponent, and we don't have a rule that can handle this. Because of that, our workaround is log differentiation. What log differentiation can do for us is it can rewrite, it can allow for a rewrite of this form so that we can actually have some rules that can come into play. But right now, as it stands, we just don't have any rule that can handle this specific scenario. So we're going to introduce natural log into this problem. That way, we can involve some log properties, such as the power property, because then once this right side is part of a natural log term, this 4x is now free to move. And once that 4x comes down, we'll have expanded methods available for us to apply. So now that I have a log expression, I'm going to bring that 4x down. And once that 4x comes down, now I'm going to look and see what derivative do I have available for me to use? What derivative method do I have available? And if I look, I have 4x times natural log of x squared plus 3x. These are two separate terms. We have a rule that can handle two terms being multiplied in terms of their derivative, and that method is product rule. So we can do f prime times g plus fg prime. The left side, natural log of y, there's a little bit of implicit going on here. This becomes 1 over y dy dx. Okay, so try that for a moment. Okay, f prime g plus fg prime. When you get to g prime, you're going to first involve natural log. And then once you're inside natural log, then you can handle this cosine's derivative, which is negative sign. So we're almost there. Our derivative looks a little messy, but that's just how things look with log differentiation. We can move the y over to the right side because we want to isolate dy dx, which represents the derivative. And once the y comes over, we're one more substitution to make is that this y can be replaced with the original problem, right? So the original equation, we can replace y with all this. All right, any questions here? All right, now let's look at a derivative of inverse at a point. See that relationship between the function and its inverse. So let's look at this one here. This is number 60 off of the packet. First packet. One second. Okay, off packet number 1. So this is derivative of inverse at a point. We're given a function. We're asked to find the slope of the g graph at -11. We have some information about the order pair, and it's established that f and g are inverses of each other. Okay. So I want to first talk about that relationship between f and g and how I like to use this diagram or chart to help map my progress here. So what I'm going to do is I'm going to put the relationship between a function and its inverse in these two regions here. And then below, I'm going to put the relationship in terms of their slope at those corresponding points. So here's my goal. My goal is I want to find g prime of -11. And really, just the way that this is kind of, I organized it, we're just kind of working our way around this diagram here. And we're going to gather information, and after enough information is gathered, that we're going to be able to make our way back to what we're looking for. So I have some information about the order pair. My order pair is -11, -3. Now, there's also an order pair of interest on the f side of things, okay? But because these are inverses of each other, we know that there is a corresponding point on the f side of things. But it's not -11, -3, right? That's not the relationship between the function and its inverse. It's the fact that their x's will be y's and their y's will be x's. So I know there's an order pair that's going to live on the f function as -3, -11. So here's what I can do if I can find f prime of -3, if I can find the slope of the f graph at -3, then that number is going to lead me directly back to my answer. Because these numbers will be numerically related to each other. These will be reciprocals of each other. So our efforts, it's going to be contained within this part. We're going to find the derivative. From the derivative, we can evaluate the derivative, find the slope at -3. And once we get to that number, we can use that number to figure out the slope of the G graph that we're looking for. So my first step is trying to get to the derivative. But before I get to the derivative, let's do a little bit of cleanup, right? What if I distribute it through and just rely on power rule? So I'm going to see what I can do to expand. So if I distribute that 1/27 through, I get 1/27 x to the 5th plus 2/27 x to the 3rd. Now my terms are nicely set up for power rule. So let's find the derivative, f prime. Coefficient stays. Variable, we apply power rule for. So x to the 5th becomes 5x to the 4th. X cubed becomes 3x squared. Clean up my derivative a little bit. And then just start evaluating the derivative at -3. And then use the calculator to get to my slope. So if my slope is 17, then that number is going to be related to what I'm looking for, right? It's always going to be the reciprocal. So 1/17. Don't change the sign, just make it a reciprocal. That's my answer here. All right, any questions? Okay, there are other examples like this in the packet, so I encourage you guys to pick out those problems that you feel like you want extra practice with, or I can go over some additional ones in our review sessions or help sessions. All right, two more things I want to go over with you. Linear approximation, and then we'll do one of these piecewise function continuity differentiable problems. So let's do a linear approximation problem. So I just created this problem. It's not in the packet. Or this, well, I just, I think it's within packet 2. I just decided to do one to demonstrate the process. So this sounds like a complex concept, linear approximation, but I just want to show you that 95% of your effort is just trying to get that tangent line equation. If you can get that tangent line equation, you've done the majority of the work. So we have our equation, y equals 2x cubed plus 1. Order pair 1, 3. It says approximate y of 1.2. So what the linear approximation is doing is we're going to create a line, create the tangent line equation, And all we're doing is we're just using this line to find the approximation. We're going to evaluate the decimal into the tangent line equation. So to find tangent line equation, we need to find order pair and slope and then point slope form. We have the order pair. We need to find the derivative to get to the slope. So let's find y prime. And then from y prime, we can find the slope by evaluating the derivative at 1. So try that. So we find the derivative. Derivative is just 6x squared. Plug 1 in, and we get a slope of 6. So now we can build our tangent line equation, right? You got your order pair, you got your slope, and now I can do point slope. Maybe I'll do a little bit of rearranging. I'll add that 3 over to the right side, just to make it a little bit cleaner, get that y by itself. But once I have my equation in terms of y, then I got one final step, and that's the approximation part of it. I'm going to put that decimal into the x. And then whatever decimal value you end up with, that's your answer. Okay, and that decimal ends up being 4.2. All right, any questions? Okay, let's do one more type of problem, and that's the continuous differentiable piecewise problems. So here's the example of that. Let's see, where'd it go? Yeah, here we go. This is in packet number 3, number 54. It says, given the piecewise function, we're told that this equation is ultimately continuous and differentiable. And it says, find the values of constants k and b. All right, let's talk about this process here. These equations are not set in stone yet because we don't know what k and b are. But we're trying to create a situation where we want these two segments or two graphs to have certain certain behavior at x equals 1. And the behavior that we want it to have is we want these two graphs to be continuous at 1. So that means we want these two graphs to share the same y value at 1, right? That's the only way we can establish continuity. And so because we want to, in a way, kind of force these two to be continuous, the way we do that is we're going to set the equations equal to each other, right? If we set the equation equal to each other, replace x with 1, then we're kind of forcing that these two y values to be equivalent. And that will help us figure out one of these variables. But then we also have another scenario, another added piece of this behavior is that not only do we want these two graphs to connect, but they must connect in a way where it's differentiable. And what I mean by differentiable, or what this means by differentiable, is we want these two graphs to connect where it's a nice smooth transition. Their slopes are also going to be matching. So we want them to share the same slope at x equals 1. It's not going to be a sudden jerk of a slope where you can obviously tell there's a sharp turn. We want it to be a smooth transition. So in order to ensure a smooth transition, we want these two to have the same slope. If we want to force the same slope, then we're going to set their derivatives equal to each other. So we're going to find the derivatives of both of these expressions and then set them equal to each other. So setting the equations equal to each other is pretty straightforward. I'm just doing x squared plus kx minus 3 is equal to 3x plus b, right? So we'll work through the left side in a little bit, but I just want to establish what happens on the right side. The right side, we got to build their derivatives and set them equal to each other. So keep in mind that k and b are constants, right? So you'll treat k and b the same way that you would if it was a 5 or 3 or 8 or 9. So let me ask you, what's the derivative of x squared plus kx minus 3? X squared becomes what? 2x. Good. Kx becomes k, right? Because if it was 5x, you would say 5. If it was 10x, you would say 10. Same thing. Kx would become k. Good. And the 3 goes to 0. Okay, good. All right, so now let's focus on this side here. 3x plus b. What's 3x plus b's derivative? Just 3, right? 3x becomes 3. The b is a constant. Treat it like you would if it was a 5 or 8, it would go to 0. Right? We don't want to treat b like a variable. We don't say b is equal to 1, right? B becomes 0. So there's our derivative side of things. Now, let's do one side at a time now. I'm going to try to work this down to hopefully just constants and k and b. So I'm going to replace every x I see with 1. So replace x with 1 here, replace x with 1 here, replace x with 1. And that's going to lead me to 1 plus k minus 3 equals 3 plus b. Continue to combine my terms and see how far I can get. I'm not able to fully resolve, but I'm able to get it cleaned up, and then we can work on the other side of things and see how that can support this equation. Because right now, right, this is why we need a second equation, because we have two variables, right? So let's turn our attention to the 2x plus k equals 3. Replace the x with 1. So I get 2 plus k equals 3. I get k equals 1. And now that information can help support this side and solve for b, right? So replace k with 1. Subtract 5 from both sides. I get b equals -4. Okay, any questions here? Yeah, that's basically all I wanted to go over today. health sessions this afternoon, tomorrow morning, Wednesday morning, and Thursday morning, mornings and afternoons. All right, if you don't have any questions, I'll see you guys tomorrow. Final review day, but you guys will take your 7th period exam if it applies to you. So good luck with that. And I'll see you guys tomorrow. All right, take care, guys.